The Douglas SBD-2 Dauntless carried more than 200 combat holes across its aluminum skin, many of them covered by field repairs. This airframe survived the Pearl Harbor attack parked on Ford Island and flew combat missions with bombing squadrons during the Battle of Midway. After absorbing heavy Pacific combat damage, the aircraft was transferred back to the United States. Its new assignment was the Carrier Qualification Training Unit at Naval Air Station Glenview. The operational objective was straightforward. New pilots needed to prove they could launch and recover on a moving deck before deploying to the Pacific Fleet. But the training environment over Lake Michigan introduced a rigid operational boundary that stripped away standard safety margins. The Navy utilized converted side-wheel paddle steamers, including the USS Sable, for inland carrier qualifications. These former civilian passenger ships were stripped down and fitted with full flight decks, but the details mattered. Wolverine used the more traditional wooden deck, while Sable carried an experimental steel flight deck. This emergency conversion created severe structural and mechanical limits. Sable's low deck height and limited maximum speed reduced the wind over deck available to the heavy Dauntless, especially when natural wind over the lake was weak. A standard fleet carrier could drive fast into the wind and give an incoming aircraft more lift at a manageable closure rate. The converted paddle steamers could not. That left a combat-weight dive bomber operating close to its aerodynamic stall limit, with almost no vertical space to recover if the pilot dropped below glide path. The flight instructors and ship commanders accepted the risk because thousands of naval aviators had to qualify before deploying to the Pacific Fleet. On June 11, 1943, Marine Second Lieutenant Donald A. Douglas Jr. initiated his landing approach to the Sable. The approach became unsafe as the Dauntless came in low and slow. The landing signal officer ordered a wave-off. As Douglas turned left and tried to add power, the aircraft remained inside the unforgiving margins of the inland carrier envelope. The left wing struck the lake surface, dragged the aircraft off its center line, and forced an immediate ditching. The Dauntless hit hard, decelerated across the water, and began to sink. Douglas unbuckled, climbed out of the damaged cockpit, and was pulled from the lake by a nearby Coast Guard rescue boat. With the engine block acting as a massive forward weight, the center of gravity pulled downward while trapped air vented from the fuselage. Without reserve buoyancy, the loss immediately removed the aircraft from service and left it as an inaccessible underwater wreck. The naval authorities marked the loss as a standard training accident and moved the next aircraft into the landing pattern. Could the aluminum airframe survive the crushing lake impact after already carrying the structural scars and fatigue of heavy Pacific combat? More than 50 years submerged in an aquatic environment can destroy thin aviation aluminum. Ocean wrecks degrade rapidly as salt water acts as a highly efficient electrolyte, fueling aggressive corrosion between dissimilar metals. A saltwater environment can attack rivets, skin panels, and structural bulkheads within a few decades. The location of the Dauntless dictated a completely different structural fate. The airframe settled on the lake bed in deep fresh water, reported in secondary accounts at about 170 feet. That depth established an important environmental boundary. In shallower coastal water, surface wave action, shifting bottom material, and winter ice could have mechanically damaged the aluminum structure. Resting deep on the lake bed, the airframe lay below the worst reach of surface turbulence. The deep lake bed greatly reduced the wreck's exposure to mechanical friction, allowing much of the aircraft's shape and surface evidence to survive over the decades. The depth reduced mechanical exposure from weather forces, but the local geography also imposed a strong thermal constraint. The water at this depth remains cold, with deep lake water often near 4 degrees Celsius, where fresh water reaches maximum density. This thermal boundary drastically slows many chemical and biological degradation processes. Biological growth, which can trap corrosive material against metal surfaces in warmer waters, is severely restricted in this cold, dark zone. The absence of sunlight limits heavy biological encrustation from blanketing the fuselage and adding structural weight. One critical local hazard for an underwater wreck is galvanic corrosion. This destructive process requires dissimilar metals, electrical contact, and a conductive fluid path between them. Lake Michigan's fresh water was far less conductive than seawater, and the cold environment further slowed reaction rates. The freshwater chemistry did not eliminate the galvanic risk, but it limited and slowed the battery effect that destroys similar wrecks much faster in salt water. The dissimilar metals across the airframe were still vulnerable at contact points, but the lake environment made severe, rapid decay far less likely. Those limits left the structure stable enough for physical evidence to survive. Factory-applied paint and operational markings survived across portions of the wings and fuselage. The original metal patches over the Pacific battle damage also remained visible, preserving the physical evidence that made this airframe unique. Because decay had slowed rather than stopped, the wreck retained enough integrity to support recovery and later restoration. Its engine section, wing structure, and tail still carried recoverable evidence. While the deep lake bed protected much of the physical integrity of the metal, the vast expanse of the bottom created an entirely different operational problem. The designated training sectors spanned large areas of open water. The depths remained dark and covered in fine silt that could conceal small details from remote sensors. Over the course of the wartime training program, many different Navy training aircraft sank into Lake Michigan. NOAA has described about 120 World War II-era aircraft lying on the lake bottom, and they were not all the same type. The environment offered little visual distinction from the surface between a standard training loss and a historically significant airframe. For any future search team, sonar could identify promising aircraft-shaped targets, but not their individual history. Side scan could separate a dense engine or wing outline from the flat mud, yet only direct inspection could close the evidence gap in 1993. Mobilizing heavy salvage equipment required money and extensive logistical coordination, so the Museum Foundation needed confidence before funding a lift. The surface team used archival research and acoustic survey work to build a list of promising aircraft-shaped targets, but recovery could not be justified until divers physically confirmed the exact bureau number. Many of these targets turned out to be geological formations, discarded marine debris, or the wrong type of aircraft. The high rate of false positives meant the team had to treat every dive as a forensic investigation. Executing this visual verification dive introduced severe physiological and environmental constraints. The target rested at a depth that significantly reduces allowable bottom time. Divers operating at this depth face rapid air consumption and the onset of nitrogen narcosis, which dulls mental acuity. The water temperature hovers near freezing, further degrading fine motor skills. Every second spent on the lake bed had to be highly structured. The diver descended down a shot line directly to the acoustic anomaly. Visibility at the bottom is entirely dependent on artificial dive lights, as ambient surface light does not penetrate to this zone. The diver located the intact shape of a dive bomber and immediately navigated toward the tail section. Military protocol mandated that the unique aircraft identifier be stenciled high on the vertical stabilizer. The cold, freshwater preservation allowed the original paint to survive, keeping the numbers intact beneath a layer of fine, suspended silt. The diver approached the tail structure with strict buoyancy control. A single misplaced fin kick would stir the lakebed mud, creating an immediate silt out that would reduce visibility to zero and force an abort of the verification dive. The diver positioned a light on the vertical stabilizer and carefully disturbed the water just above the metal skin. Sweeping a gloved hand through the water created a localized current that lifted the fine sediment away from the aluminum surface. Scrubbing the metal directly carried the risk of flaking off the fragile paint, which would permanently erase the exact proof required to identify the aircraft. The number on the tail read 2106. The diver documented it, checked the surrounding tail structure, and began the required decompression ascent to the surface. This physical confirmation separated this specific airframe from the background noise of standard training losses. Verifying the number 2106 satisfied the primary objective and authorized the transition from a search mission into a heavy salvage operation. The identity was locked, but the operational hazard now shifted to the structural integrity of the airframe. Once identity was confirmed, the salvage teams had to determine how to safely hoist a flooded, fragile relic to the surface without tearing it apart. With the target identity secured, A&T Recovery lifted the aircraft from the lakebed in January 1994 on behalf of the Naval Aviation Museum Foundation. The operation had to manage weather, depth, diver safety, and the severe geometry of a flooded airframe whose trapped water weight altered its center of gravity. The primary constraint during the extraction was structural load distribution. Aluminum wing roots and fuselage spars are engineered to carry aerodynamic loads in flight, not careless suspension loads after decades underwater. The aircraft was not designed to be picked up by its external skin. To reduce the risk of tearing the airframe apart, the recovery team used a controlled rigging plan that spread load across stronger structural areas and minimized shock loading. The most critical handling constraint came at the surface, where buoyancy gave way to gravity and trapped internal water could overload the weakened structure. The final lift had to be slow enough for water to drain while the crane transferred the emptying shell onto a custom wooden cradle that supported the fuselage evenly. The extraction was complete, and the artifact was secured. The next question was how much of its original combat history had actually survived the ordeal. When the SBD-2 Dauntless arrived at the assessment facility, the inspection team confronted an immediate structural contradiction. A typical aviation artifact recovered after 51 years underwater usually requires the total replacement of dissolved skin panels and shattered bulkheads. However, this airframe defied the standard degradation models. As technicians initiated the preliminary teardown process, they discovered a level of preservation that forced a complete pivot in how the project would be managed. The immediate priority was stabilizing the airframe and mapping its physical condition. The aircraft arrived at the facility still resting on its extraction cradle, packed with dense lake sediment that filled the wings, the engine cowling, and the lower fuselage. Technicians had to meticulously flush this mud out using low-pressure water streams to expose the primary structure. This phase of the inspection required intense operational discipline. Removing the sediment too aggressively carried the risk of washing away delicate operational stencils or tearing loose fragile internal components. As the mud cleared, the true state of the metal emerged. The aluminum skin lacked the heavy pitting or exfoliation that routinely destroys ocean wrecks. The main wing spars, the heavy engine mounts, and the cockpit canopy rails retained their original structural integrity. With the internal airframe clean, the assessment team faced a complex forensic problem. The aircraft carried significant physical trauma across its exterior, but interpreting that trauma required strict evidence discipline. The inspectors had to distinguish between the structural bends caused by the 1943 ditching impact in the lake versus the historical 1942 battle damage sustained during the Pacific Air War. The left wing exhibited clear compressive buckling and twisted metal. This specific damage aligned perfectly with the geometry of striking the water at stall speed during the missed approach to the paddle wheel training carrier. The kinetic energy of the crash transferred directly through the wing root, permanently warping the leading edge and shearing rivets along the lower spar. In direct contrast to the blunt force ditching damage, other sections of the fuselage and tail displayed completely different physical signatures. Assessors mapping the skin panels found concentrated clusters of jagged perforations. More importantly, they documented the survival of original patched combat damage. Across the fuselage, squadron mechanics had riveted crude metal plates over bullet and shrapnel holes. These patches were not uniform factory modifications, nor were they the result of shifting lake bed pressure. They were the hasty, functional repairs made during the intense combat operations of the Pacific Campaign. The airframe still carried the exact operational scars from its engagement with the Japanese carrier fleet. The survival of these field modifications fundamentally changed the inventory profile of the aircraft. Standard salvage operations often yield a compromised shell that requires fabricators to manufacture brand new aluminum sections to replace lost material. During a typical restoration, the line between an original historical artifact and a modern replica can become heavily blurred as entire sections are replaced. After the Dauntless arrived in Pensacola, the inspection team found that the aircraft retained extraordinary recoverable evidence, including its battle damage patches and portions of original paint. Later restoration work incorporated a high proportion of original or period-correct material, but the safest record is not that 90% of BuNo 2106 itself survived untouched. It is that the restored display preserved the identity and combat evidence of the Midway veteran while using restoration material where necessary. The assessment shifted the project away from a standard rebuild and toward conservation of the surviving evidence. The question now became what protocol could stabilize the airframe without erasing the combat record. The National Naval Aviation Museum faced a fundamental choice when approaching the stabilization of the recovered Dauntless. The curatorial team had to decide how to restore the airframe for permanent public display without erasing the evidence that made it irreplaceable. Standard aviation restoration can involve stripping away faded paint, hammering out dents, and replacing compromised aluminum panels. This traditional approach yields an aircraft that looks as though it just rolled off the assembly line. But on this airframe, the visible scars were the story. The museum did not leave the aircraft as an untouched wreck. Before public display in 2001, it underwent extensive restoration that preserved the combat patches and selected original paint evidence while returning the aircraft to a stable static configuration. Executing this restoration strategy proved drastically more complex than a simple cosmetic rebuild. To stabilize a compromised airframe, technicians could not simply hide jagged combat damage beneath a flush new skin and call the work complete. The aircraft had to be cleaned, dried, inspected, repaired, treated, and reassembled in a way that kept the visible evidence intact. Moisture, sediment, corrosion products, and weakened fastener lines all had to be managed carefully after the aircraft left the lake. The restoration team worked slowly because each original patch and surviving paint area carried evidentiary value. Leaving the crude, non-standard field repairs intact required custom engineering solutions. Those improvised repairs did not align with original Douglas factory blueprints. To support these irregular sections without altering them, the restoration team had to design specific internal braces. They carefully reassembled the aircraft, ensuring that the structural load of the display was carried by the internal spar network rather than the fragile, battle-damaged exterior skin. This component-by-component stabilization demanded an extreme labor investment, 70,000 hours of work. The time reflects the operational friction of preserving history rather than replacing it, especially when a bent and patched wing had to be disassembled, chemically treated, and reassembled without sacrificing original evidence. The final display made that methodology visible. The fuselage still displays the metal patches placed over wartime damage, while selected unrestored panels and surviving paint traces preserve a direct link to the aircraft's earlier service life. Douglas SBD-2 Dauntless Bureau No. 2106 currently resides at the National Naval Aviation Museum in Pensacola, Florida. In that final form, the aircraft remains a restored museum display bearing the linked scars of Pearl Harbor, Midway, and Lake Michigan.